So just a brief review of the concept of definite integral. So definite integrals are a means of summation of finite areas infinite number of times. So to get a specific area. So like yesterday, we discussed how, the area of the circle, is, sum of the areas of the triangles formed by a regular polygon. So we computed and showed this, and then we showed how integral a to b f of x dx can be obtained by taking this interval a to b, dividing into n number of subintervals, and finding these rectangular areas, and then making n tend to 0. Sorry, n tends to infinity, and then we get the area under the curve from a to b. So we discussed that this sigma notation, sigma of I equal to 1 to n, this particular notation, this is used for discrete number of terms, discrete terms. However, this integral sign, which is elongated s, it represents summation, and it represents on over a continuous interval. So this limit n tends to infinity, sigma of I equal to 1 to n, this is replaced by this integral sign, and this delta x becomes dx when n tends to infinity. So that's how we get integral f of x dx. And so another angle of another way of looking at the definite integrals is you take a very thin strip whose initial point is at a distance x and whose width is dx. So the function value of at x is f of x. So when we expand this and see this here, it is like f of x into dx gives us the area of the rectangular strip, thin rectangular strip. Summation of all such rectangular strips from a to b, all such infinitesimal rectangular strips from a to b, is the definite integral a to b f of x dx. Then we discussed how this antiderivative and the concept of definite integral are connected by this Newton-Leibniz formula. Integral a to b f of x dx is the value of the antiderivative at b minus value of the antiderivative at a. And we discussed the antiderivative function can be written as capital F of x is equal to integral a to x f of t dt. And differentiating this will give us this function f of x. And we discussed one very important formula yesterday. This will be used very often, that the derivative of integral of u of x to v of x f of t dt is f of v of x into derivative of v of x minus f of the lower limit multiplied by the derivative of the lower limit. Then there were application of these theorems for discontinuous functions. And then we ended with the geometrical interpretation of definite integrals. Now, what happens if areas are above the x-axis or below the x-axis? So areas above the x-axis will have positive sign, areas below the x-axis will have negative sign. So here we discussed one example of integral sine x integrating from 0 to pi by 2 once, then integrating 0 to pi, then integrating 0 to 3 pi by 2, then integrating 0 to 2 pi. So 0 to pi by 2, the value of integral is 1. From 0 to pi, the value of integral is 2. From 0 to 3 pi by 2, the value of integral is 1. Why? Although the area is getting added, this portion of the area will have a negative sign because the function itself has a negative sign here. So f of x times dx product will be negative. So although this portion of the area, this half from pi to this 3 pi by 2, the area is 1, but it has a minus sign. So the minus sign here, plus 1 minus 1 gives us 1. And then this portion also area is 1, but with a negative sign again, so minus 1. So you get plus 1 minus 1 minus 1. So it's 0. So sum of the areas is 0. So that's why we get integral this 0 to 2 pi sine x dx. We get the value as 0. So we did this up to here, this point. So we'll proceed from here. Okay. So now comes, okay, based on antiderivatives, how do we find the definite integral? So we'll start today. Evaluation of definite integrals. So evaluation of definite integral. So we go by the standard forms, the standard ways of indefinite integral. So first one is reducing to standard forms. Reducing the integrand to standard forms for which we have an antiderivative. So this is the first part. So let's take this example. Integral 0 to pi under root of 1 plus cos 2x dx. Okay. Now purposely this example has been taken. It is not out of an accident. Now this example will tell us although we are using standard forms, we need to be very careful with the signs. So let us look at this. Now we know, so let this be I. Now we know that cos 2x is 2 cos square x minus 1. So which implies 1 plus cos 2x will be equal to 2 times of cos square x. So we get I is equal to integral 0 to pi under root of 2 cos square x dx. Now the tendency is to write this as under root 2 comes out, then 0 to pi, tendency is to write this as cos x dx. This is wrong. Why? Why is this wrong?
Sir, because from pi by 2 to pi cos is negative.
True.
Thus the value will cancel. So
No, but why is it wrong? From pi by 2 to pi cos is negative, but why is this wrong?
because cos square x was inside, so we should take modulus of cos.
Good. Because this is because under root of x square is equal to modulus of x. Because under root by itself is positive. Even if cos x is negative, let's say cos value is minus half. So minus half whole square becomes 1 upon 4. 2 into 1 upon 4 is 1 upon 2. Under root will become 1 upon under root 2. It will not become minus 1 upon under root 2. Okay. See, very important. Again, I'm repeating. Here earlier, when we were doing limits, I told this, but again, I'm repeating. See, if x square is equal to a square, let us say, then x will be either plus a or minus a. Why? Because it will be, let's say a is a positive quantity. We write x as plus or minus root of a square, which is plus or minus a, given a itself is a positive value. But under root of a square, which we don't know what the value of a is, or to be more precise, under root of x square will be modulus of x, because here the root is associated with positive sign only. In the previous case, x square is a square, so x is either plus under root of a square or minus under root of a square. But here it's already given under root of x square. So no matter whether x is positive or negative, this under root will be positive always. So here we need to make that distinction. So here the correct way of writing is integral 0 to pi modulus of cos x dx. Okay. Integral 0 to pi modulus of cos x dx. Then the answer will be, of course, we need to split into two now. I will do it directly also by graphs, but here we need to split this into two. 0 to pi by 2 cos x dx plus integral pi by 2 to pi mod cos x dx. All right. So cos x is positive in the when x lies in the first quadrant. So when x varies from 0 to pi by 2, cos x is positive. So we get integral 0 to pi by 2 cos x here. And between pi by 2 and pi, the second quadrant of x, cos values are negative. So modulus of a negative will be minus of the negative value, minus of that expression. So this is the difference in the interval. So we get integral. So now we can integrate it. Integral of cos x is minus sin x, sorry, plus sin x from 0 to pi by 2 minus of sin x from pi by 2 to pi. So this becomes sin pi by 2 is 1 minus sin 0 is 0 minus sin pi is 0 minus sin pi by 2 is 1. So you get 1 plus 1, which is 2. So answer is 2 under root 2. The same problem, if we are not careful, we'll get answer as 0. Now there's a simple trigonometric substitutions and calculation. There is nothing. I see this question and I will directly tell the answer is 2 root 2. Why? Because first step I calculate up to here, under root of 2 cos square x. The next step, this is right. So we need to take from here. So this we need to omit. This is wrong. This is wrong. So we need to omit this. This is right. So under root 2, 0 to pi mod cos x dx. Directly I'll tell this answer is 2. Why? Look at the graphs. So that's the power of graphical understanding. Now y equal to cos x. Now we know that this is same as, shifting. This is sine pi by 2 minus x. All right, cos x is sine pi by 2 minus x, or that means we are shifting the graph of sine x towards the positive, or you can say x sine of pi by 2 plus x is also cos x. All right. Now we are shifting the graph leftwards. I'll just show this. This is sin x. Okay. Now, when we have to show cos x, I will do just a second. Okay. Okay, look here. This is the graph of sine x. Now, I will do sine of x plus sine of x plus a. Okay, now as a varies, okay, the graph shifts either from right or left. Depends on a is, if a is negative, graph shifts towards right. If a is positive, graph shifts towards left. Now, what is pi by 2? Pi by 2 value is 1.57. So I'll fix a at 1.57, approximately 1.571. Now look at cos x. Now cos x and sine of x plus pi by 2 are one and the same. Okay, so we have just, cos x is just shifting the graph of sine x by pi by 2 towards leftwards. Now yesterday we did the, now I'll hide the sine x, cos x graph and sine of x plus a graph. Now yesterday we found the integral from 0 to pi by 2, integral 0 to pi by 2 sine x dx. The answer was 1. Okay, so now same, when integral 0 integral cos x from this minus pi by 2 to 0, the value will be 1, and from 0 to pi by 2 again the value will be 1. Excuse me. So from 0 to pi by 2 the value again will be 1, because that's the integral, it's symmetric. So this is the value of integral. We can find out, that is simple integration. So what I'm trying to say is, now I will show you how did I calculate that this particular integral is 2 straight away. So now when I take a modulus, modulus of cos x, this function, this in orange color, is the modulus of cos x. What is happening? Modulus means modulus of a number. It gives the absolute value of the number without the sign. So when we do modulus of x, if cos x is positive, it will remain positive. But if cos x is negative, it will convert those values to positive. It will multiply it with -1. So what happens? We get this. This negative portion has been transformed to the positive axis. So this is the value of modulus of cos x. Now modulus of cos x from 0 to pi, from 0 to pi, the values of cos x, it is 1 plus again symmetrical 1. So this is what I wanted to explain. So if we have a graphical understanding So this graph is the graph of modulus of cos x. All right. Now this region here, this integral, this area is 1 and this area is 1. Because I know what is integral of sine x. So from there, from 0 to pi by 2. So from there, I'm deducting integral of cos x from 0 to pi by 2. Symmetrical portion. This is 1 and this is 1. So 1 plus 1 is 2. So directly here itself, by just visualization, I can say that this integral is 2. I didn't have to do all these things. So if you are good at graphs, you can save a lot of time. That's what I wanted to communicate. So this integral, what we discussed, is a very important integral for two reasons. One, it tells that although the integral is very, very simple, but we have to consider the interval of integration and we have to take the signs appropriately. Okay. Clear? Now we'll go to another one. Evaluate integral minus 1 to 1 maximum of 2 minus x, comma 2, comma 1 plus x. Now you will not have in your examination, you will not have the freedom of using a grapher like either Desmos or GeoGebra. You will have to do by hand. So I'll do this by hand only. Now minus 1 to 1. This is 0, 1, minus 1, and here also 1, 2, 3, so on. Minus 1, minus 2, minus 3. Now, this is 2 minus x, y equal to 2 minus x. So, y-intercept is 2 and the slope is 1, minus 1. Slope is negative. So, when x is equal to minus 1, the value is 3. When x equal to 0, the value is 2. And when x equal to 1, the value is 1. So this is this straight line. This is y equal to 2 minus x. Now the second line is y equal to 2. This is the second line, y equal to 2. And third line is y equal to x plus 1. So slope positive. So when x is 0, y is 1. When x is minus 1, y is 0. And when x is 1, y is 2. So this will be this line. Okay. So now we have to find the maximum of. So if you see in this particular interval, minus 1 to 1, the maximum value is of this point, this line, 2 minus x. This is the maximum. And between 0 and 1, which is maximum? both these graphs are lying between y equal to 2. So y equal to 2 is the maximum here. This is y equal to x plus 1. So when we have to take the maximum, see how I'm calculating the area. All right. When I have to take the maximum, it will be here. It will be this. In this region, this is the maximum. So my function will be 2 minus x. This will be the maximum function. In this area between 0 and 1, the function will be 2. So between -1 to 0, because the uppermost is the function, I need to calculate this shaded area. And between 0 and 1, I have y equal to 2. So I'll have to calculate this entire rectangular area. Okay. So my integral will be very simple. The value integral -1 to 1 maximum of 2 minus x, 2 and 1 plus x dx will be area of this total shaded portion. First one is a trapezium, half into sum of the parallel sides into the distance between them. Sum of the parallel sides, this is 3, this is 2. So half of 3 plus 2 times the distance between the parallel sides is 1. Plus we have this rectangular area. Height of this rectangle is 2, width is 1. So 2 into 1. So we have 5 upon 2 plus 2, which is 5 plus 4, 9 upon 2 is the value of the integral. And we did not do any integration. Okay. If we have to do it by integration, we have to do it like this. So this was just a graphical method. If we have to do it by the normal method of integration, so we have to go about in this manner. Of course, we'll have to look at the graph and then do it. From the graph, we get between -1 and 0. This 2 minus x is the largest function. And between 0 and 1, 2 is the largest function. So we have split this integral from -1 to 0 and 0 to 1. And the largest function we have written in both the cases. Now we can integrate this. Integrating this, we can integrate individually 2x minus x square upon 2 from -1 to 0 plus 2x from 0 to 1. So substituting 0 and substituting -1, we get this, plus substituting 1, we get 2, and substituting 0, we get minus 0. Now this is minus 5 upon 2 times -1, that is plus 5 upon 2 plus 2, which is 9 upon 2, which is the same what we got. So instead of integrating, I've just calculated the area. So this is a very graphical way to approach a problem of definite integral, which is very easy. And if we understand the concept of definite integral, we'll be able to easily solve it. Okay. Next question. one more on this one. Evaluate integral of pi by 2 to pi 1 minus sin x upon 1 minus cos x. This again an integral. We need simplification for this one. So again, reducing to standard forms, the solution. So write the denominator, write the numerator as 2 sine x by 2 cos x by 2, and the denominator will be 2 sine square x by 2, because cos x is 2 cos square x by 2 minus 1, or it is 1 minus 2 sine square x by 2. So from there we come. So this is minus pi by 2 to pi 1 upon 2. We get cosecant square x by 2 minus sine cancels, 2 cancels, cos upon sine is cot. Now this we have got into standard forms. Integral of cosecant square x. What is integral of cosecant square x? It is minus log mod cot x. Okay, differentiate this 1 by cot x into derivative of cot x is minus cosecant square x. You will get this. And this is, yeah, cos by sine. Derivative of sine is cos. So you'll simply get log mod sine x by 2 upon half. Here, actually, we'll get cot x divided by half. So half and half gets cancelled. So this will be the integral. I'm sorry, here it should be cot x by 2. Now apply this from pi by 2 to pi. So we get minus log one second. Okay. Log mod cot pi. I'll explain how to do this one. Minus log mod cot pi by 4. Okay. Next is twice of log mod sine pi by 2 minus log mod sine pi by 4. So cot pi is cos pi upon sine pi. This goes to infinity actually. So this goes to infinity and this goes to 1. So this is 0 minus 2 times log 1 is 0 minus log 1 upon under root 2. Answer.
Sir, I have a doubt, sir. Sir, isn't integral of cosecant square x equal to cot x?
What is derivative of cot x?
Is cosecant square x?
Minus.
Oh, minus cot. No, I mean, my point is you have written integral of 1 by 2 cosecant square x by 2 as minus ln of mod cot x by 2. I did not understand that.
Oh, it's directly cot. I'm sorry. I'm sorry. Yeah, it's not log mod. It is just cot. Thank you. Thank you. Cot x is cot x is minus cosecant square x, right? I'm sorry. So when we differentiate this, you get minus cosecant square x. Derivative of cot x is minus cosecant square x by 2 times half. So derivative of this is this. You're right. So now when we apply, one second. So we get here minus of cot pi by 2 minus cot pi by 4. Yeah. So what we get here is minus of cot pi by 2 is 0 minus cot pi by 4 is 1. So this is 1 minus 2 minus of minus is plus and log 2 to the power minus half. So which is 1 plus 2 into minus half log 2. So we get 1 minus log 2 as the answer. Thank you. All right. So this is the integral. This is the integral. Again, this is reducing into standard forms and substituting. Next. So what we did 3 examples of reduction into standard forms, but taking care of the interval of integration. Second is you don't have to worry about the evaluation of the integral as long as you can calculate the area. And third one is again one of the trigonometric reducing into standard forms and integrating. Now, next type is integration by substitution, but we need to be very careful. How do we substitute? So, two things that we need to pay attention to. By substitution, the limits of the integral change. Or we should first find the antiderivative by substitution and then substitute back the original variable and find the full antiderivative and then apply limits. Otherwise, the limits will change. Okay, so we will take an example of that. And second very important one is that the substituted function must be continuous in the interval of integration. The substituted function must be continuous in the interval of integration. So let's take examples for integration by substitution. Okay. Let's take a simple one. All right, I'll take evaluate this integral 0 to pi by 4 cos x upon 1 plus 4, or yeah, 1 plus 4 sin x, a simple one, cos x upon 1 plus 4 sin x, a very simple one will take. Now let us substitute sin x as t. This will imply differentiating cos x times dx is dt. However, we cannot write 0 to pi by 4 dt upon 1 plus 4t. This is wrong. Why? Because these 0 to pi by 4 were the limits on x. X is changing from 0 to pi by 4. When we write like this, it means that t is changing from 0 to pi by 4. So we cannot write it like this. So the way we need to write is, we have to find the value of, say, when x is equal to, simple, when x is equal to 0, then t is equal to sin x, which is sin 0 is 0. And when x equal to pi by 4, t is sin pi by 4, which is 1 upon root 2. Okay. So this is I is equal to, now I will change integral t equal to 0 to 1 upon root 2. I've changed my I've changed the limits on the variable. The variable itself has changed. Now cos x dx becomes dt by 1 plus 4t. Now this is 1 upon x form. So this is log mod 1 plus 4t upon 4. This will be the integral from 0 to 1 upon root 2. This will be log of 1 plus 4 by 4 into 1 upon root 2 minus log 1 plus 0 upon 4. So what we get is 1 upon 4 log of 1 plus 2 times under root 2. This is the answer. So here we could make this substitution because sin x equal to t. This is the substitution we are making. And sin x is continuous function throughout the set of real numbers. So it is continuous on this interval 0 to pi by 4. So we could make this substitution. Sometimes the substitutions we cannot make, they become absurd. So we will see in what case. Yeah. Look at this example. I is integral minus 1 to 1 dx by 1 plus x square. This is a standard integral. We know the value of this integral. We can find this out. That is not easy, not difficult. Now let us consider this. The question here is the substitution x equal to 1 upon t valid? This is the question. This is a question. Now, because you see here, if you put x equal to 1 upon t, right, then what you get is, if x equal to minus 1, then t is 1 upon x, which is equal to minus 1. If x equal to plus 1, then t is also equal to plus 1. So only thing is, you check this, and dx, what will be dx? Dx is minus 1 upon t square dt. Therefore, I is integral minus 1 to 1 t, I'm writing from minus 1 to 1, dx is minus 1 upon t square dt by 1 plus 1 by t the whole square, because x I replace by 1 by t, so I get 1 by t whole square. So upon simplification, what I get is, this t square cancels in the denominator. I get minus sign, minus 1 to 1 dt by t square plus 1. Now this integral is same as this integral, just that x is replaced by t. The integral, as long as, because in definite integrals, the variable does not matter whether it is x or t. You get the antiderivative and you substitute in the antiderivative f of b minus f of a. That's what you do. So this doesn't matter. So this is also equal to I. So we get 2i equal to 0, which means I should be equal to 0. The question is this correct? Answer. It's a common mistake that students make when they go for substitution.
So this is not correct, because 1 by t is not continuous throughout minus 1 to 1.
So yeah, our substitution is t is 1 upon x. All right, we are taking 1 upon x, or you can say, so when x varies from minus 1 to 1, you will come across the value of x equal to 0, at which point this is a discontinuous function. So the substituted function is discontinuous. So no, a big no. All right. This is because the substituted function t equal to 1 by x is discontinuous at x equal to 0 in this interval minus 1 to 1. Clear? So this substitution is not valid. It is invalid. The substitution is invalid. So in reality, the value of this integral, we know this is a standard form. The integral, this is the integral of the antiderivative of 1 upon 1 plus x square is tan inverse x. Now we apply the limits -1 to 1. So tan inverse of 1 minus of tan inverse of -1. So tan inverse of 1 is pi by 4 minus of minus pi by 4. So this is pi upon 2 is the answer. This answer is correct answer. What we got is this, which is wrong. This is wrong. So in integrals, we need to be very careful of the substitution. 2 points here, very important. First point, when we are substituting, we should ensure that the limits of integrals also change according to the new variable. And the second point is we cannot make substitutions which cannot exist within this given interval, which has a discontinuity. So we cannot take such substitutions. So these are the 2 points, 2 important points in integrating by substitution. Next, integrating by parts. This is simple. So this is also applicable for different integrals. So example, we'll take integral of log x from 0 to 1. Now, the second function, integrating by parts, taking the second function as unity. Second function is 1. So we get first function into integral of the second, all right, minus integral of, I'm doing antiderivatives only, just see, derivative of the first times integral of the second. Students make common mistakes is they apply the limits randomly. So when they are integrating here, sometimes they integrate and apply the limits inside. No, after you evaluate the full antiderivative, you apply the limits. You will be safe. So you get x log x. Integral of 1 is x. So now we apply from 0 to 1. So we get 1 times log 1 minus 1 f of b minus f of a. Okay. X log x minus x. Now, okay. Now, log, very important. This again, I'll deal with this in detail. Now, log x tends to minus infinity as x tends to 0. At x equal to 0, log is not defined. So we will have to do this for this one. Limit x tends to 0 plus x log x minus x, because directly you cannot substitute the limit. You will get 0 minus 1 minus, the second part is 0, this part limit is 0, but here we will have to apply L'Hospital's rule for limits of miscellaneous functions, which we have done in the previous chapter. So minus 1 minus limit x tends to 0 plus derivative of log x is 1 upon x, and derivative of 1 upon x is minus 1 upon x square. So we get minus 1 plus limit x tends to 0 plus of x. So minus 1 plus 0, which is equal to minus 1. So why did we do this? We did this because x is tending to x is going to 0 and function is not defined there. So we cannot directly substitute this. We have to take limit as x tends to 0 from the right. So answer is, it is minus 1. So this is integration by parts. For many other functions, we'll give examples, meaning I'll give exercises. So we just need to do integration by parts, find the full antiderivative, and then substitute the limit. Then you will not make a mistake. Otherwise, there are 3 integrals. The first integral, then the second integral, within that there is another integral. So you have to be careful in applying the limits. Next comes, all right, all these are there, no problem. All these standard methods are there. But there are some very beautiful properties of definite integrals which are used to find out the integrals without doing calculations many times. Okay, so definite integrals by standard methods, transformation, by methods of substitution, integration by parts, and now the properties. These are very useful and beautiful properties. Okay. The very first property, these properties are used, and mostly the questions that we get use the properties of definite integrals. So the first property, integral a to b f of x dx is same as integral a to b f of t dt. So what this says is change of the variable does not matter. It is not substitution, by the way. It is just x is replaced by t, or x is replaced by y, or x is replaced by p. It doesn't matter. Change of the variable does not matter. It is not that x is substituted as some other function. X is substituted as t. That's all. Now, if we interchange the limits a to b f of x dx and b to a f of x dx, then the integral sign changes by minus 1. Okay, the sign changes by minus 1. The logic is very simple. So suppose we are integrating a function from a to b. Function value is positive, and when we are moving from a to b, the increment delta x, or as delta x tends to 0, the increment dx will be positive when we move from a to b. However, if we move from b to a, then this delta x or dx that we are calculating, this will be negative. Okay, because a smaller value minus a larger value, this will be negative. So this times the function will be a negative value. So when we move from a to b to find area, or when we move from b to a to find area, the value of the integral changes by a minus sign. Now, third property is splitting the integral. So property 3, I'm explaining here. Integral a to b f of x dx is integral a to c f of x dx plus integral c to b f of x dx. Now two scenarios arise. Let us study them. One, let us say the function is like this. This is y equal to f of x. And this is a, this is b, and there is some in between value c. So now integral a to b f of x dx is talking about this total area. Integral a to c f of x dx is talking about this red area, red striped. This one is pencil stripe, this is red stripe. And c to b is this area. Integral c to b f of x dx is this area, striped in green. So the area that is striped with the pencil from a to b is equal to the sum of these two areas. All right. So that's how this holds true. So this particular integral a to b f of x dx is a to c f of x dx plus c to b f of x dx. So this one holds true. Now let us look at the second possibility in this. Now let us say this is a to b, but the function extends to, this is a, this point is b. Now let us say c is this point. Now when you say a to b, again with the pencil shade we mark, the left hand side is integral a to b f of x dx. This is the shaded portion. This is the shaded portion. Now integral a to c, I'll mark with red. It is this total area. So this shaded portion and this extra portion from b to c, that will be a to c. Then from c to b, now c is outside. So when you do c to b from the second property, this will be a negative value as compared from b to c. So this will be a negative value. So this integral c to b f of x dx will cancel out this integral b to c f of x dx. So what we are left with, so total area minus this area, we are left with this area shaded with the pencil. So in both the cases, whether c lies inside or c lies outside, the integral a to b f of x dx will be this area shaded with the pencil shade or the gray shade. So did you understand? So here we say C may lie either inside or outside of the interval. Generally, we think this is valid when C lies inside the interval. Of course, the functions should not go through any discontinuity. Function should be continuous throughout the region of discussion. Okay, did you understand this property? It's a simple property. The first part is straightforward to understand. The second part is tricky, but it is the same. So this is valid whether C lies inside or outside of the interval AB. Next, fourth property, a very useful property. Integral 0 to a f of x dx is same as integral 0 to a f of a minus x dx. Why does this happen? Of course, the proof you can take easily and prove it. You know, I'll not go through it. From your intermediate or class 12 text, you can take a minus x as t, then minus dx is equal to dt. So dx is minus dt. And when x is equal to 0, t is equal to a. When x is equal to a, t equal to 0. So you will get a to 0 minus f of t dt, which reverses, and you will get 0 to a f of t dt, which is same as this. So LHS equal to RHS, you can show by that particular substitution. But I want to show this graphically. See, if this is f of x, pay very careful attention. Let's say this is f of x, right? From, oh, yeah, it's talking from 0 to a. Now, whatever value you find of when x is equal to 0, all right? This is f of 0. Now, when you put x equal to 0, you get, for the second function, you get f of a. So this is f of a. This is f of x. This is y equal to f of x. So put x equal to 0, you get f of a. And put a equal to 0, you will get f of 0. Okay. So you get a function that is decreasing. At what we get is this type of a function, f of x and f of a minus x, are symmetric about the line x equal to a by 2. At x equal to a by 2, both values will be equal. And across that, they will be symmetric. So what happens is, so this is y equal to f of x, and this is y equal to f of a minus x. It is the same area, just that they are symmetrically placed about x by 2. This area and this area, they are the same region. Okay, so that's why this is an important property, very often used. very, very often used. And we will do a few problems straight away on this. This fifth property is just an extension of this. This is a mistake written here. Just a second. This is integral. There's a mistake here. This is integral a to b f of x dx is integral a to b f of a plus b minus x dx. Okay, this is 0 to a. This is just an extension of this. Instead of 0, we are shifting the limits of integration from a to b. Same logic, what I told here is valid. The same principle of symmetry about the center is valid. So here the symmetry will be about x equal to a plus b by 2. At that point, it will be symmetric. Now, two more properties, the sixth and the seventh one. Okay, the fifth one was this integral a to b f of x dx is integral a to b f of a plus b minus x dx. The sixth one, very, very important property, so many times asked, and it solves our problems very simply. Integral minus a to a. If the limit is symmetric, the interval of integration is symmetrically situated about the origin. Integral minus a to a f of x dx is equal to twice of integral 0 to a f of x dx if f is an even function, and it is 0 if f is odd function. Okay, so very simple. Sin x is odd, cos x is even, so we can take those examples, very straightforward. So let's look at sin x. Sin x from, say, minus pi by 2 to pi by 2. We'll look into that. As an example. And then we will also look into cos x, because cos x is an even function, sin x is an odd function. So let's look at that. From minus pi by 2 to pi by 2. Okay. So this is function f of x equal to sin x, which is an odd function. So integral minus pi by 2 to pi by 2 sin x. So this is an example of an odd function. So odd functions, we know, are symmetric about the origin. They lie in the opposite quadrants, and their signs are, the graph of odd functions lie in the opposite quadrants, and they're symmetric about the origin. So what happens, this integral value here, we know that this portion we have calculated, the value will be 1, but because it is below the x-axis, the value will be minus 1. Here, the value of this integral will be plus 1. So minus pi by 2 to pi by 2, the integral value will be 0. So whenever there is a odd function, the graphs between minus a to a will have opposite, the areas will have the opposite sign and they will be symmetric. So it will be 0. Whereas for an even function, for like cos, so integral minus pi by 2 to pi by 2 cos x dx, because it is even, so from minus a to a, it will be 2 times of 0 to pi by 2 cos x dx. Why? Because this area is positive plus 1 and this area is positive plus 1. So 1 plus 1 equal to 2. So this area, this total minus pi by 2 to pi by 2 is same as twice of 0 to pi by 2 cos x dx. It is twice of this portion. Clear? So this is about even and odd. And again, another property of symmetry, the last one we will do now, and then we'll do problems. Another of symmetry is integral 0 to 2a f of x dx is equal to twice of integral 0 to a f of x dx if f of 2a minus x is equal to f of x. This is similar to the odd symmetry, odd and even problem, just that here the symmetry is considered about the point x equal to a or the line x equal to a. This is 0 if f of 2a minus x is equal to minus f of x. So in the previous case, when you say even or odd function, here we get f of minus x is equal to f of x. And here we get f of minus x is equal to minus f of x. And there are algebraic full detailed proofs you can find in any textbook, but I'm giving you a graphical picture. My idea is when you look at a problem, you should be able to visualize the problems graphically as far as possible and immediately come to the solution without having to actually solve the integral. That is why I'm giving a graphical point of view. So this is what it is. Now, what this kind of a function, you see, it has a similar pattern of this. When we say f of 2a minus x is equal to f of x, then this means symmetric about x equal to a line. All right. So you can see this. Okay. So this is 0 to 2a. All right. 0 to 2a. So put x equal to a, f both will be 2a minus x will be 2a minus x will be a and x will be equal to a. So at this point, both coincide. But otherwise, when x equal to 0, f of this function will be f of 2a. This is f of 2a. this 0. And when x equal to 2a, this is f of 0. So it will be same as this value f of 0. So this is y equal to f of x. And this curve, it will be symmetric. You can see this is f of 2a minus x. So both of them are symmetric about this line, x equal to a. You just flip it around this line, you will get one function, flip one function, you will get the other. So both are symmetric. Oh, sorry. Actually, just a second. I made a mistake here. Actually, the graph will be like this. The graph will be, I realized when I did, the graph will be symmetric about x equal to a. So let us say there is this point x. Then at the same distance from 2a, you will get 2a minus x. So value of the function at x and 2a minus x will be the same. So the graph of the function will be symmetric about this line x equal to a. So when you do this integral 0 to a and integral a to 2a, both will be equal. So therefore, integral 0 to 2a will be twice of integral 0 to a. It will be twice of 0 to a. Now, on the other hand, if f of 2a minus x is equal to minus f of x, then f is symmetric, or I should say odd symmetric, about a comma 0. Now just see this. Okay. All right. So this is a, this is 2a, this is 0. Now let's say this is any point x, this is 2a minus x. Whatever is the function value at x, 2a minus x will have the same function value but with a negative sign. So the graph of this function will be like this. Okay. Okay, we'll draw much better graph. Even I will change it this way. So what we see is the graph will be symmetric. This portion, shaded portion, will be equal to this shaded portion, but with a negative sign. So when you add, the integral will be 0. Okay. So let's do some problems on this. Okay. The property 3, we will use examples, problems. First one, find integral 0 to 4 pi, modulus of sin x. How will you find this? Okay, I'll give you time, 2 minutes. Tell me the answer. Tell me the answer. Integral 0 to 4 pi, modulus of sin x.
Sir, 8.
Good. Good. Very good. Others? Say. For this, you just look at the graph of modulus of graph of sin x, we know. This is graph of sin x. Mod sin x will be all positives. The negative portions will be reflected on the positive sign. So modulus of sin x this will be modulus of sin x. This is mod sin x graph. So now we want from 0 to 4 pi. So this is the graph of mod sin x. And this visually you should picturize. You don't have to actually solve. I'll do that by solution also. Now, here we know that we have calculated that this integral we have already done. This integral 0 to pi by 2, this is plus 1. So plus 1 plus 1 is 2. So just this one portion of the curve, one crest, this portion is 2. Now, when you go from 0 to 4 pi, you get 4 such loops for this curve. So 2 into 4 is equal to 8. So the answer is 8. Straightforward. All right. Otherwise, if you don't have to do graphically, then it will look like this. This is sin x from pi to 2 pi, and then from 3 pi to 4 pi, it will be negative. So this has to be split like this. If we have to do without the graphical interpretation, modulus of sin x, we'll have to do integral 0 to pi mod sin x dx plus integral pi to 2 pi mod sin x dx plus integral 2 pi to 3 pi mod sin x dx plus integral 3 pi to 4 pi modulus of sin x dx. And then remove the modulus. Between 0 to pi, sin x is positive. So mod of a positive expression will be the expression itself. Between pi to 3 pi, pi to 2 pi, sin x is negative. So modulus of sin x will be minus of sin x. When you try to do it algebraically. Then from 2 pi to 3 pi, again, sin x is positive. So it will be plus sin x dx. And between 3 pi to 4 pi, it is minus sin x dx. And then we need to compute the antiderivative of sin x is minus cos x. So 0 to pi, then minus of minus cos x from pi to 2 pi plus minus cos x from 2 pi to 3 pi plus or minus cos x from 3 pi to 4 pi. Okay. So this way we get, minus 1, minus of minus 1, minus of minus 1. So you get 2. Each time you substitute, you will get the value 2. So 2 plus 2 plus 2 plus 2 is 8. You will get the value as 8. So which is better? Which is better? If you understand graphical method, it is better, provided you know integral 0 to pi by 2 sin x dx is 1. From there, everything else follows. Okay. So this was based on property 3, where a larger interval is split into various subintervals. Clear? Next. Question 2. Now this is on property 4. Look at this. This is again some standard integrals. Integral 0 to pi by 2 dx upon 1 plus tan x. Let's evaluate this integral. So let us use, when you see this, use property 4. What is that? Integral 0 to a f of x dx is same as integral 0 to a f of a minus x dx. So what we get from here is, what is tan of pi by 2 minus x is cot x. Therefore, I is integral 0 to pi by 2 dx by 1 plus tan x becomes, upon applying this property, 0 to pi by 2 dx upon 1 plus tan pi by 2 minus x by applying property 4. And this becomes integral 0 to pi by 2 dx by 1 plus cot x. This cot x I will write as 1 upon tan x so I'll get integral 0 to pi by 2 tan x by 1 plus tan x dx. So this is also I. This is I. This is also I. This portion is also I. I'll do I plus I. When I do I plus I get 0 to pi by 2. 1 upon 1 plus tan x, the first integral here. And the second I will write as 0 to pi by 2 tan x by 1 plus tan x. Now, because the limits of integration are same, we can add the integrands. One upon 1 plus tan x plus tan x upon 1 plus tan x dx. When we add this, obviously what we are getting is the common denominator, and when you add the numerators, the numerator turns out to be the same as the denominator. So upon cancelling, you get 1. Integral of 1 is x. From 0 to pi by 2, you apply the limits, you will get pi by 2 minus 0. So you get 2i is equal to pi by 2. So I is equal to pi upon 4. I is equal to pi upon 4. Got it? Look at this again. We are using property 4. Integral 0 to a f of x dx is same as integral 0 to a f of a minus x dx. And we are continuing to do this. We applied that, simplified that, summed it up, and solve the integral. Okay. Now, same model, similar models. You will have okay, I'll mark it as 2b I equal to integral 0 to pi by 2 dx by 1 plus tan power n x. All right, doesn't matter. It becomes cos x 1 by tan. It doesn't matter whether it is n equal to 1 or 2 or 3. It is valid for all. I equal to integral 0 to pi by 2 tan power nx by 1 plus tan power nx. It is same again, exactly the same problem. Oh, sorry, this is 2c. Integral 0 to pi by 2 dx by 1 plus cot power n x, same as this, exactly the same procedure. You can take any one of them and do it. 0 to pi by 2 cot power nx by 1 plus cot power nx. Then elaboration, extension to sine. Sine power nx by sine power nx plus cos power nx. Same, divide by sine x, numerator and denominator. You will get 1 by 1 plus cot power nx. You will get this form, 2D form. If you divide by cos power nx, you will get tan power nx divided by tan power nx plus 1. That will be this 2c form. So this can be converted to this, or just leave it as it is. Just the same procedure you do, you will get integral 0 to pi by 2 cos power nx by sine power nx plus cos power nx. All right. All these integrals have the answer pi by 4. Just practice any 2 or 3 of them. Understand how others can be reduced in terms of one can be reduced in terms of the other. All have the answer pi by 4. So sometimes this n is given as half, that is under root sin x upon under root sin x plus under root cos x. So when you see that under root sign, don't get you know, don't get confused. This is just the standard form. Okay. Look at question 3. Please do this. I want all of you to do this. I'll give time. Integral 0 to 1 x into 1 minus x to the power 99 dx. Let's see who will give the answer first. One answer so far. Others? Okay, 2 minutes. So just look at this. 1 minus x whole power 99. Yeah. To expand this by binomial theorem, you will get 100 terms, multiply with x, and you have to keep track of all the coefficients, plus sign, minus sign, very difficult. So use this property. Integral 0 to a f of x dx is same as integral 0 to a f of a minus x dx. So therefore, I will be integral 0 to 1, x becomes, replace x by a minus x. So a here is 1. So replace x by 1 minus x, a minus x. And here replace x by a minus x. All right. I have replaced x by a minus x. So integral 0 to 1, 1 minus x, 1 minus 1 becomes 0, minus into minus becomes plus. I get x power 99. I have avoided the entire binomial theorem expansion. Now this becomes very simple. X power 99 minus x power 100 dx. So the integral will be x power 99, x power n integral will be x power n plus 1. So x power 100 upon 100 minus x power 101 upon 101. Apply the limits 0 to 1. We get 1 power 100 by 100 minus 1 power 101 by 101 minus 0 minus 0. So we get 101 minus 100 by 100 times 101. So we get 1 upon 10100. This is the value of the integral. Okay, this is the value of the integral. It's 6, but I will take just 5 or 10 more minutes to do two or three problems, simple ones. So this was a very simple example using the fourth property. Now, one more type on the fourth property that is very useful. That's why we do this. So find out what is integral 0 to pi x sine x by 1 plus cos square x dx. In this problem, we cannot use substitution because x is here. If x was not there, cos x could be written as t, then minus sin x dx could be written as dt. So from there, we could have done something, but here you have x. So how to do this problem? Again, use the same property. Integral 0 to a f of x dx is integral 0 to a f of a minus x dx. So this implies we have I is equal to integral 0 to pi minus x times sine of pi minus x by 1 plus cos square pi minus x dx. Just 0 to pi minus x times pi minus x times, this is sine of pi minus x is sine x, and cos of pi minus x is minus cos x, but because of the square it becomes cos square x. So I is equal to pi times sine x. So integral 0 to pi sine x by 1 plus cos square x dx minus integral 0 to pi x sine x by 1 plus cos square x. What is this? This is the original integral I. This is the original integral I. So I plus I becomes 2I is pi into integral 0 to pi sine x by 1 plus cos square x. Now, how to do this problem? Now, cos 0 is 1, cos pi is minus 1. So how to do this problem? Substitute, put cos x equal to t. This gives minus sin x dx is dt. So sin x dx is minus dt. Now, what happens when t, x and t So if x equal to 0, then t is equal to 1. And if x equal to pi, then t is equal to minus 1. And cos this t equal to cos x is a continuous function from 0 to pi. So this substitution is valid. So we get 2i is equal to pi times 1 to minus 1 sin x dx is minus dt upon 1 plus t square. So this minus sign, if you remove the minus sign, the limits will reverse. So minus 1 to 1 dt upon 1 plus t square. So 2i is pi times, this is tan inverse t from minus 1 to 1. So this is pi times tan inverse 1 minus of tan inverse minus 1. So 2i is equal to pi times tan inverse 1 is pi by 4 minus of minus tan inverse 1 is minus pi by 4. So we get pi times pi by 2. So we get pi square by 2. Therefore, I will be pi square upon 4. This is an important problem for practice. It has many components. Property 4, then repetition of integral. So it goes to the other side. And while solving this, substitution. And after substitution, then property 2. So this is a very important problem to practice, to get familiar with the properties of integration. Then one more. Look at this. This is a good integral. Evaluate this integral. Integral minus root 2 to plus root 2. 2x power 7 plus 3x power 6 minus 10x power 5 minus 7x power 3 minus 12x square plus x plus 1 upon x square plus 2 dx. Looks a very big integral. Now, what do you do in this? Use integral minus a to a f of x dx is equal to twice integral 0 to a f of x dx if f is even, and this is equal to 0 if f is odd. Okay, so now let us split this. I will split these into odd and even components. I will take all odd terms, that is odd powers of x, 2x power 7 minus 10 x power 5 minus 7 x cube plus x divided by x square plus 2, plus I will take the even powers, 3x power 6 minus 12x square plus 1 by x square plus 2. So this is an odd function. This is an even function. So that apparently huge looking integral becomes very simple. There's an odd function because denominator is even, but the numerator has all odd powers. So we get integral minus √2 to √2, the odd function, plus the even function, so this integral, because of this being odd function, this integral goes to 0. Because this is an odd function, and based on this property, for an odd function, this is 0. And because this is an even function, this becomes twice of 0 to a. 0 to √2, 3x power 6 minus 12x square plus 1 by x square plus 2 dx. Now we can simplify this further. 3 I take common. So 3x square, if I take common, I'm left with x power 4 minus 4. I can simplify further. 3x square into x square minus 2 into x square plus 2. So we get a very simple expression, 0 to √2. This cancels, x plus 2 cancels. We are getting 3x square into x square minus 2 plus 1 upon x square plus 2 dx. Now I'm writing the integral directly. The first term is 3x power 4. So 3 into x power 5 upon 5 minus 3 to 6x square. So plus 1 by a tan inverse x by a. This is the antiderivative of the third term. So now substitute the upper limit under √2 whole power 5, that is under √2 whole power 4 times under √2, that we'll see now. This is 2 √2 whole cube plus 1 by √2 tan inverse √2 upon √2 tan inverse 1 minus 0 minus 0 minus 0 plus 0. Second limit, when you substitute, it is 0. So you get 2 into 3 by 5 into 4 √2 minus 2 into 2 √2 is 4 √2 plus 1 by √2 by pi by 4. So 4 √2, 4 √2, if we take common, you will get 3 minus 5, it is minus. So minus 8 √2 upon 5. So the answer is pi upon 2 √2 minus 16 √2 upon 5. You can simplify it further, but this is the answer. Again, these are for practice. This is a problem for practice. So I'll stop here for today.